Welcome back. In this video, we'll be looking at Theorem 2.2.6. In the last example, we took a shortcut at the end. Instead of proving that the linear transformation was onto, instead of finding its image, we just used a dimension argument. We used the rank nullity theorem to prove that it is onto just because of dimensions. All right, so we want to get something like that going on a larger scale, and that's what the following theorem will give us. All right, so the following theorem generalizes the invertibility theorem of matrices that you've seen in linear 1. All right, so theorem 2.2.6, invertibility theorem for linear transformations. I'm going to take V to be a vector space of finite dimension, dimension 1, n, sorry, I read this one. Let T from V to W be a linear transformation. So first of all, if T is an isomorphism, then the dimension of W is the same as the dimension of V, it is n. All right, so if two vector space are isomorphic, they must have the same dimension. All right, second, assume that the dimension of W is n. Then the following statements are equivalent. So you remember this from linear 1. It means as soon as one is true, they're all true. As soon as one is false, they're all false. So first statement, T is an isomorphism. Second statement, the kernel of T is just a zero element in V. Our equivalent nullity of T is 0. All right, so that's statement B. You could also look at the image of T, proving that the image of T is W, or that the rank of T is n, the whole dimension of W. That's enough to show it's an isomorphism. All right, so we will prove this theorem, but to do so, I kind of contracted half of the work out to you guys. So to prove this theorem, we'll need the following result, which you will prove in a worksheet and an assignment. All right, so consider a linear transformation, T from V to R. If I have a linearly independent set, a linearly dependent subset of V, then T of S, which is just applying T to all of the elements of S, is also linearly dependent. So if you start with a linearly dependent set and you map it forward, it's still linearly dependent. All right, now assume that T is 1 to 1. If S is a linearly independent subset of V, then T of S, again, same thing, you apply T to all the elements, is also linearly independent. All right, so the proof of this lemma will be included in worksheet and in assignments. All right, let's prove the invertibility theorem for linear transformation. I'm going to start by proving 1. I'm going to assume that T is an isomorphism. All right, so I'm going to take a basis for V. All right, so I claim that TB, which is TV1, TVN, is a basis for W. All right, we sort of did this already. We did it when we proved the rank nullity theorem. All right, when we proved the rank nullity theorem, it's the same result, except that now the kernel is going to be 0, and so we don't have that part. All right, so let's prove it again. So I need to prove that TB is linearly independent, but BV is linearly independent, and T is 1 to 1. And so the lemma right here the proposition, sorry. So that means by proposition point 2, T of BV is linearly independent. Second thing I need is I need TBV to span W. All right, remember W, since we have an isomorphism, is actually the image of T. So for W and W, we know that W is TV, and so that's T. We have a basis, so it's T A1V1 plus ANVN. I'm going fast because we've already done this before. And so W is in the span of image of T. All right, so we have a basis for T, and so its dimension is N. All right, now we need to prove that once you know that the dimension of W is the same as the dimension of V, which we've proven here, but once you know this, the dimension of V and dimension of W are the same, then to prove that T is an isomorphism, you have these options right here. So what I'll do is I'll first prove these two are equivalent, and then I'll show that if it's an isomorphism, then you get them and vice versa. All right, so we will first show that B and C are equivalent. All right, so by the rank nullity theorem, I have that the nullity of T plus the rank of T equals the dimension of V, which is N. All right, so if the nullity is 0, which is, let's look, it's statement B. If the nullity of T is 0, that means, so this is 0, this needs to be N, and vice versa. Rank of T is N. All right, so if the kernel of T is just the 0 element, that's the same as the image of T being W. All right, so you can see why the rank nullity theorem was important. It gave us interesting criterion to prove that T is an isomorphism. All right, so now we have two things left to prove. We'll start by proving that if you have an isomorphism, then B and C are true, and then we'll prove that if B and C are true, then we have an isomorphism. These are not hard. We've done all the hard work before. So if T is an isomorphism, that's what we assume. So let's put assume T is an isomorphism. Then T is 1-to-1 and T is onto. But if T is 1-to-1, actually let me put this here so I can continue. If T is 1-to-1, that means the kernel of T, we've proven that if T is 1-to-1, then the kernel of T is 0, and so the nullity of T is 0. And T is onto, that's the same as the image of T being W, and so the rank of T being N. All right, so that was easy. That we've done all the hard work. The same will be true for part B. It's exactly the same reasoning in reverse. So assume that if we have B and C, so assume the nullity of T is 0, and the rank of T is n, then if we have the nullity of T is 0, that means the kernel of T is 0, and so that means that T is 1 to 1. And if the rank of T is n, that means the image of T is W, and that means that T is onto. All right, so we have 1 to 1 and onto. T is therefore bijection. It is invertible, and so it is an isomorphism. All right, I think this proof is much less complicated than the rank nullity because we use the rank nullity. We've put all the work there.